Good afternoon. It is Dr. Gangadar Chugar, Senior Lecturer, Department of Applied Sciences, Chandigarh College of Engineering and Technology, Diploma Wing, Sector 26, UT, Chandigarh. Today, we are going to discuss gas laws. In this lecture, we are going to consider these following points. Number 1, definition of gas laws, SI units and technical units of measurable properties of the gases, Boyle's law, Charles law, combined gas law, gas constant and its units, Avogadro's hypothesis, and some applications of gas laws in the engineering fields. As we know, the condition of any gas can be characterized in terms of its measurable properties such as volume, pressure and temperature. The change in any of its measurable properties affects the others. Therefore, the relation between the measurable properties of fixed mass of a gas or the relation between the measurable properties of fixed mass of any gas are called gas laws. So, those measurable properties are volume, pressure and temperature. So, as you have already studied in the first unit, the SI unit of volume can be derived as meter cube or cubic meter. In spite of the cubic meter, there are some other units are also used such as decimeter cube or liter. So, 1 cubic meter will be equal to 1000 decimeter cube or 1000 liter. So, we can prove this, since 1 decimeter is nothing but 10 to the power of minus 1 meter. So, you can have this. And SI unit of pressure, as you know, SI unit of pressure is force, defined as force per unit area, and it is Newton per square meter, and that is given a special name Pascal. So, 1 Newton per meter square is equal to 1 Pascal. We write it as 1 Pa and written as Pa, but read as Pascal. So, and SI unit of pressure, that is Newton per square meter or Pascal, is smaller one, and therefore, in SI units pressure, a larger SI unit has been accepted. For example, kilonewton per square meter, kilonewton per square meter or meganewton per square meter. So, 1000 kilonewton per square meter is equal to, we can write it as 1 mega Newton per square meter, since 1 mega means 10 to the power of 6. So, there is a customary to express the pressure even in terms of bar. So, bar is another larger SI unit of pressure commonly used for practical purposes. So, 0.9807 bar equals to 98.07 kilonewton per square meter. A pressure below, there sometimes we have to measure the pressure less than atmospheric pressure. So, a pressure below or very close to the atmospheric level measured in millimeters of mercury or millimeter of water. Here I would like to just discuss the technical unit of force. You are a technical students, therefore, it is quite important to know the technical units as well. So, unit of force, as we know SI unit, force when applied to a body having mass of 1 kilogram gives it an acceleration of 1 meter per square seconds. It is given a special name, as you know, Newton. It is a derived unit and it is represented by capital M. So, 1 kilogram meter per second square is nothing but 1 Newton. However, in technical units, the unit of force is defined in expressed in terms of kilograms force, kgf we write it as, but it is read as kilogram force. It is that force which when applied to a body having mass of 1 kilogram, it gives acceleration of 9.80665 meters per second square, and approximately we take this as 9.81. So, 1 kilogram force is 9.81 Newton. So, it is also called as kilogram weight, but g varies from place to place, therefore, we cannot equate this one. However, we will in the next slides we will see the unit of mass, the SI unit of mass in kilograms, and it is represented by kg. However, technical unit of mass is defined in terms of kilogram force. It is that mass of a body which acquires an acceleration of 1 meter per square second under the influence of 1 kilogram force. This kilogram force is technical unit of force, as we have seen in the last slide, technical unit. So, this is the technical unit of mass, and it is here it is derived unit. It is not fundamental when we take it as a derived unit here when we are talking about the technical unit. If we, and it is evident from the definition that unit of mass, that technical unit of mass is g times greater than the mass of 1 kilogram. So, if m represents the technical unit of mass and m is smaller m is mass in kilogram divided by acceleration due to gravity, this gives you the technical unit of force, technical unit of mass. So, if you are expressing the mass in the form of a kilogram force, then there is a constant here which is equal to acceleration due to gravity, which is merely number in order to calculate the technical unit of mass. So, F is equal to m into a m into f, where is m is the mass force, weight is equal to this technical unit if you are expressing this one, and this will be g value, this is gravitational acceleration. So, you will study these details in the next classes, higher classes. So, just to remind you, we have given this one, and there is one example which we have solved here. So, it is just for your information we are showing here. However, this is not important for first semester students, but higher semester students can be benefited. As you go to higher semesters, these units you will be quite oftenly using this. Now, it is important to note the technical unit of pressure. Practical purpose, the pressure is expressed in kilogram force per square centimeter. Okay. So, it is known as a technical atmosphere. 1 kilogram force per square centimeter is equal to 98.07 kilonewton per square meter or 0.9807 bars. So, these are the conversion terms, and the instrument what we use for the measurement of the pressure is manometers or pressure gauges. Okay. And see the technical unit, of course, the unit of SI unit of temperature, it is the intensity of the heat, because when a heat is applied to a body, its hotness will increase, and when heat is removed, its hotness will be decreased. So, the SI unit of thermodynamic temperature is Kelvin, and it is denoted by capital K. So, the practical purpose, the melting point of water is taken, that is 273.15 Kelvin to be exact, at 1 atmospheric pressure. So, it is a melting point of ice. So, for practical purpose we use degree Celsius also. Okay. So, there is a conversion factor, you have studied this also in the first chapter, that Kelvin if you have subtract 273.15. So, you will get a degree Celsius. If you have degree centigrade, add 273.15, you can convert the temperature into Kelvin scale. So, these are other Fahrenheit is also there, and Rankine unit also there, but for this lecture we will just restrict it to these two units, degree Celsius and Kelvin. So, there is one point which you are supposed to remember, 1 Kelvin is equal to 1 degree Celsius or 9/5 degree Fahrenheit or 9/5 degree Rankines. So, Rankines. So, now we will pass on to the gas laws. See, the first law what we are going to discuss is Boyle's law. So, what Boyle's law states that this is the first quantitative relation between volume and pressure of the gas, which was studied by Robert Boyle as early as 1962. So, the when you just see this graphic here, see the pressure is varied of a given mass of a gas. This mass of the gas taken in this cylinder is fixed and the pressure is increased or decreased here. However, temperature remains constant. So, the variation of pressure and volume at constant temperature can be put in the form of a law, and this is what the Boyle did. So, Boyle's law states that at constant temperature, see the temperature is being kept constant. So, the volume of given mass of a gas, see mass of the gas you have taken, that is also constant. The given volume of the given mass of a gas varies inversely as its pressure. So, increase the pressure, if you increase the pressure, volume gradually decreases. So, this is inversely proportional. So, V, if it is V is the volume of the gas, then P is the pressure of the gas, of course at constant temperature, and the relation between volume of the given mass of a gas and pressure can be written V inversely proportional to P at a constant temperature. So, this graphic illustrates that, see as the pressure decrease, volume will increase. So, as the pressure decrease, volume will increase, and as you increase the pressure, volume gradually decreases. So, the relation between the volume of given mass of a gas and the pressure is Boyle's law, which can be stated as, the Boyle's law states that at constant temperature the volume of given mass of a gas varies inversely as its pressure. So, V is inversely proportional to P at constant pressure. This equation, this can alternatively be stated, the product of the pressure of the given product of the pressure and volume of given mass of a gas remain constant at constant temperature. If I multiply the volume and pressure of the given mass of a gas at constant temperature, it will be a constant. This is another way of writing mathematically the Boyle's law. So, this is the statement you should remember. Boyle's law states that at constant temperature the volume of given mass of a gas varies inversely as its pressure. So, we can represent this by another equation, P1V1 equals to P2V2 at constant temperature. So, if you have a pressure and volume at particular constant temperature. So, if you multiply the product of the pressure and volume, that will be equals to the pressure and volume of the same gas at P2 pressure and P1 according to this equation. So, how do we represent this classic Boyle's law? By graphic representations. Suppose if we plot 1 over P, reciprocal of pressure versus reciprocal of volume, versus pressure, and keeping the temperature constant throughout the experiment, keep the temperature constant, and mass of the given mass of the gas must be constant. Take a fixed mass of the gas, vary its volume and check its pressure. Okay. So, plot the graph of reciprocal of volume versus pressure of the gas at constant temperature. So, I have taken 3 different graphs here to make you that these are at different temperature, but one experiment is at constant temperature. This line indicates the experiment conducted at constant temperature, that is T naught. Throughout the experiment, this one it is T1 is the constant temperature, and how it is varying. So, inversely this is inverse, and this graph is showing as the temperature increases here, the slope of the graph is also increasing. See T naught, T1, T2, T2 is highest. So, these are different temperatures, but for a particular experiment the temperature is constant. Okay. Suppose if we plot a graph of volume versus pressure, here we are taken reciprocal of volume versus pressure. Here we are straightway taking the volume of the gas and we are studying this. So, we get the curve as you have seen in the previous slides. See here there is a curve. The same way you will get here the practically if we plot the graph of volume versus pressure at constant temperature, we get the curves. So, these are at 3 different temperatures, this variation is shown in the graph. Okay. So, next the some examples, of course, numerical examples are not directly asked in the examination for first semester students, but anyway these are helpful for the studies. So, you can solve these numerical problems which are easy. Just I have given here, you can use the P1V1 equal to P2V2, that is the one form of Boyle's law, and we can solve these such type of simple problems on the Boyle's law. The next law what we are going to discuss is Charles' law. So, there is a Charles' law describing how gases tend to expand when heated, was formulated by Joseph Louis Gay-Lussac in 1802, but he credited this to Jacob Charles. So, and this is known by Charles' law, known right now it is called as Charles' law. Okay. Charles' law states that, see this graphics also illustrate, for a fixed mass of a gas at a constant pressure, pressure is kept constant here, mass of the gas taken is constant, we are going to vary its volume and see how the temperature vary, or you vary the temperature, study how the volume is varying. So, this the relation. So, Charles' law, if just see the graphic, it illustrates that as the temperature of the gas is increased, the volume will also increase. See the, and what must be kept in mind, there must be a pressure constant and mass of the gas also constant. So, then we can say this Charles' law. So, Charles' law states that at constant pressure, the volume of given mass of a gas varies directly as the temperature, direct relation, direct dependence. Okay. So, the statement of Charles' law, again you read it once again. Charles' law states that at constant pressure the volume of given mass of gas varies directly as the temperature. So, this is can be written mathematically, if V is the volume of the given mass of a gas at constant pressure and capital T is the temperature of the gas, then we can write V is proportional to T at constant pressure. Or if you simplify, keeping this removing this proportionality, you will get a constant. So, the ratio of volume of given mass of a gas to its temperature is constant at constant pressure, that can be mathematically expressed, V by T is constant. So, if you have two conditions, V1 pressure at V1 is the volume at T1 temperature, and V2 is the volume of the gas at T2 temperature, then they must have the equal to constant, and we can equate this, or else V1 T2 must be equal to V2 T1. So, this is, so I just remind you, the Charles law is states that at constant pressure the volume of given mass of a gas varies directly as the temperature. So, we can have a graphic representation of the Charles law. See here, the temperature in degree Celsius is taken, T in degree Celsius. When we plot the graph of variation of given mass of a gas, volume of the given mass of a gas as its temperature, then as the volume increases, the temperature will also increase, or as the temperature increases, the volume of the gas will also increase, provided the pressure and mass of the gas is constant. So, this is fixed. Let us say this is at P naught pressure. Suppose if you keep the P1 is the pressure, so again for a same gas or different gas, but mass must be constant as long as this experiment is concerned. So, again it shows that the volume of given mass of a gas increases with increase in temperature. So, if you take this all three, it illustrates for fixed throughout one experiment there is a fixed mass of a gas, and here as you change the pressure, see this is a P naught, P minus 1, P1. So, P1 is less. So, lesser the pressure you have maintained for a given fixed mass of a gas, and studying the variation of volume of given mass of a gas with the temperature, then the slope of the graph will be more. These are isotherms. Okay. So, now this is also very important graph that you see. It means that, look at this, when we plot the graph of volume versus temperature, for a fixed mass of a gas at constant pressure, see volume increases with increase in temperature, and it is noticeable here that at 0 degree Celsius the volume of a given mass of a gas at constant pressure is not equal to 0. So, temperature is 0, whereas the volume is not 0. So, this is a noticeable point. You have to notice this point when we plot the graph of volume versus temperature in degree Celsius for a fixed mass of a gas at constant pressure, then no doubt the volume will increase with increase in temperature. However, when the temperature reaches 0 degree Celsius, the volume of the given mass of a gas or fixed mass of a gas you have taken can never be equal to 0. It is, let the volume occupied by the given mass of a gas at 0 degree Celsius be V naught. So, if we try to extrapolate that, and we will be end up with an interception of this line on the x axis at minus 273.15 degrees Celsius, and this is what is called as absolute 0, and it is a hypothetical or theoretical temperature. A theoretical temperature, and it is absolute 0. It is absolute 0 so called because as you reduce the temperature, as you know from this experiment, volume keeps on decreasing, and the volume will reduce to 0 when we reach a hypothetical temperature or a theoretical temperature of minus 273.15, and it will be a 0 volume. So, if you say you have taken gas and it is a volume is going to be 0 at minus 273.15, that means matter should not exist at that temperature, is not it. So, however, it is not possible to just take a gas and reduce the temperature to minus 273.15 and matter must be disappearing. It never happens, because thermodynamics says the first law, matter can neither be created nor be destroyed. So, that is why it is a theoretical temperature. So, theoretical temperature. So, these are the temperature which are achievable, but this is quite difficult, because here the volume reduces to 0, and hence this temperature is called absolute 0, where the volume of the given mass of a gas equal to 0. So, that is practically very difficult to achieve, and it is not permitted as per the first law of thermodynamics. But at 0 degree Celsius, it is very much evident that the volume of given mass of a gas can never be equal to 0 at constant pressure. So, therefore, let it be V naught. So, let the volume of the gas at 0 degree Celsius be V naught. So, this is useful for us, because to define, and from this graph it is, when you see the practically, if you see, yeah, for every 1 degree rise in temperature or less in when 1 degree rise in temperature or 1 degree fall in temperature of a given mass of a gas at constant volume, then its volume V naught, V naught is the volume of the given mass of a gas at 0 degree Celsius, and that will vary to the how many times, 1 divided by 273.15 times the volume of the gas at 0 degree Celsius. So, therefore, if we if the volume of given mass of a gas at T degree Celsius is V T, then we can write a volume of a given mass of a gas at T degree Celsius is equal to volume of that gas at 0 degree Celsius plus the V divided by 273.15 times the temperature. This much volume it will occupy extra, therefore, both can be equated here. And if we simplify mathematically, at the end we can substitute 273.15 T in this expression. This is mathematical simplification, and if I put this as T here, capital T, and 273 as T naught, means absolute 0 here naught. So, then this equation 4.4 will take the form V T is equal to V naught T divided by T naught, and further we can simplify this into V T divided by T must be equal to V naught divided by T naught. That means, here V is proportional to T, that at constant pressure, and which is the Charles law. Therefore, Charles law can alternatively be said as follows. Charles law can alternatively be defined in this fashion: the pressure remain constant, the volume of given mass of a gas is directly proportional to the its temperature in Kelvin. Look at that, it is capital T now. Capital T means temperature in Kelvin, thermodynamic temperature. So, therefore, a new scale of temperature was initiated called Kelvin scale of temperature or thermodynamic temperature. Kelvin scale, as we have already known. See, degree Celsius, if you have, you want to convert that Kelvin to degree Celsius, subtract 273, and if you want to convert Kelvin to degree Celsius, then add 273 to your degree Celsius temperature. So, this is how the Kelvin was able to establish the unit of thermodynamic temperature, and there will be some examples. 20 milliliter, this is a work, you have got to work out this one, this type of examples. So, which can be easily worked out with the help of a formula what we just recently seen, V 1 upon T 1 equal to V 2 upon T 2 based on Charles law. So, we can combine the two laws, Boyle's law as well as Charles law. When we combine, see, recollect what the Boyle's law states. Boyle's law states that at constant temperature the volume of given mass of a gas varies inversely as its pressure, and Charles law states that at constant pressure the volume of given mass of a gas varies directly as its temperature. Let us take a gas at a condition P 1 pressure, V 1 volume, and at T 1 Kelvin temperature. This is capital T. Now, we are supposed to express temperature only in Kelvin, thermodynamic temperature. Therefore, T 1 is capital K, that means Kelvin, the pressure, volume and absolute temperature. So, that is the reason why they are written absolute temperature here of a fixed mass of a gas. Keep in mind, in all these statements the